So this right here is going to be the solution to our question. So let's go through the first part of it. So I did this in another screen, but I will go through it once again on one side as well. So I have the answers here, but I will go ahead and do it in front of you. So right here, let's start with part A. So part A, what do we have? We have a temperature of being 140. And so, well, I guess I should say what the directions are. It says for H2O, so for water, determine the specified property at the indicated state. Locate the state on a sketch of the TV diagram. So we'll do the TV diagrams in a second, but right now I want you guys to be able to understand this first part. We'll do the TV in a second. So it says part A, we have a temperature equal to 40, or 140, and a volume of 0.5. So let me go ahead and write that. So we have T is equal to 140 degrees C. And we have volume, little v, specific volume, is 0.5 meters cubed per kilogram, right? So that is what we know for part A, right? So what we know for part A is this. And so now what we need to do is we need to figure out where it is located on the chart, right? Like that's our biggest problem, is we need to find where it is located. And so I'm pulling up this right here. These are the tables. So we were given a temperature and a specific volume, which means that since we weren't given a pressure, we have to use the temperature table, right? So your first stop at every time you're trying to find a state point, and this is going to be basically every question that you do in thermodynamics, is that we need to first figure out where it is. And your first stop should always be the saturated tables. It should be this right here. Either a temperature table or a pressure table. And so, with that, we have to now go find 140 degrees Celsius on the chart. So, we go down the temperature chart here. So, obviously, these are all temperatures. 45 is this one, so we must go to the next page. And right here is our 140 line, right? So, 140 is the shaded blue line right there. Okay? The one that I highlighted. So now that we know that, we have to then compare what else we know. So we have a volume of 0.5 meters cubed per kilogram, right? So let's go over to the specific volume line. So the specific volume line, let me go ahead and make this smaller then, so we can do them both at the same time. But while we're doing that, I'll keep talking a little bit. So the specific volume line shows us that. It shows us that the specific volume of the saturated liquid is 1.0797 times 10 to the negative third. And the saturated vapor value is 0.5089. Okay? So, if we take that, right, and plug our value into an inequality here, we have VF, or little vf, is less than our value, which is 0.5, but our value is also less than the saturated vapor value, which is Vg. And this is at, or at sign as I usually write it, T equals, or at T1, right? Our temperature 1 is 140. So what that means is that our value is inside of the saturated region, right? Because it is inside of these two numbers. Now, it is very close to inside of those numbers. I agree with you. It is not if it was 0.5089, then you could say it is saturated vapor. But it is not. There is still a little bit of liquid in there. So, because of that, the question asked for the pressure. That's what we were supposed to find here. If you guys remember from the prompt, it says find P in bar. So, if we have to find the pressure here, how do we find the pressure? Well, the pressure here is whatever the saturation pressure is, because remember, inside of that saturation curve, the pressure and temperature do not change when you get to it, right? Unless you increase the pressure, right? So these things don't change when you're inside of it. So right here at 140 degrees Celsius, the saturation pressure is 3.613, which is this value right here in that column of pressure bar. So 3.613 is our answer for the first one. Does everybody see how I got that? Because the fluid is saturated, or it has met the saturated condition, P1. This is how I usually write it, so I'm going to write it how I would write it. So P1, here, let me move this back. P1 is equal to Psat at T1. So essentially, our pressure is equal to the saturation pressure at temperature 1, and our temperature 1 is 140 degrees, right? So to say that in, I guess, English is that it is, because the fluid is inside of here, we have proved it because our value is less than Vg, and it's also greater than Vf. P1 is equal to the saturation pressure at temperature 1. Okay, hopefully that made sense. Now, we are going to go to the next one. So that was it, and our answer was, here, I guess I should write our answer as well. Sorry. P1 is equal to 3.613 bar. So that is our answer for the first part. Now let's move on to the second part. So the second part of this question asked for, with a pressure given of 30 megapascals and a temperature given of 100 degrees Celsius, find the specific volume. This was the trickiest one out of all of them, right here. So this one was the trickiest one, and I'll show you why in just a second. So what do we know? This is the very first thing we have to do. Once again, T1 is equal to 100C. P1 is equal to 30 MPa, which is also equal to 300 bar, right? So those are our two things that we know off the start. So what did I tell you guys is the first step? The first step is to go straight to the saturation tables, right? To figure out if we're in between there. So we need to go to either one of these, right? So I think what you guys did is you guys probably went and tried to find 30 megapascals or 300 bar on this table. And it is not on this table, right? Did somebody do that? So 300 bar is not on this table. And so that's what you have to do now. So this right here should have been a hint, but since you guys aren't experienced in the tables, this is that should have been like a red flag. But that's okay, because what you do is you can also go to the temperature table. If we go to 100 degrees Celsius right here, you will see that at 100 degrees, so now we're at the temperature table, just to be clear. If you go to 100 Celsius right here, this line, the saturation pressure is 1.014. Is our number higher than that? You say yes, and you're correct. So what does that mean? Where are we located on the saturation curve area, the TS diagram? Where are we located? So right there, that is the trap. Because, remember, for the temperature table, the relationship is inverted. If we are over that number, we are subcooled. We are compressed liquid. But on the pressure table, we are superheated if you're over the number. So that was why this question was the trickiest one. Is that here we are a subcooled liquid because we are over this number. So the relationship flips on the temperature table or the pressure table. I mentioned this last class, but obviously we didn't get to do an example of it. But it flips here. And so what we have to do is we now have to go to the subcooled region tables, right? Subcooled liquid tables. So if we go to the subcooled liquid table, so there's two ways to do this, and we can do it a different way. But we'll talk about that when we get to the next chapter, I guess. But essentially, I told you that compressed tables aren't used very often because they're not. Because they have really odd pressure jumps, and so they're hard to actually use. So I'll go to it right now. So at one, and also It should also be noted that this is the boiling point of water. Essentially, at 1 atmosphere, this is what we walk around at. So essentially, at 1.014 bar, the boiling point is near 100 degrees C, and we are at 30 megapascals. So that was the other trick. So we have to go past the superheated tables, right? And we have to go to the compressed liquid tables. So compressed liquid starts here, and we have to go find 300 bar, which is right here. And so if you go over at 100, and you drop to here at 1, so our answer, let me see. So let me see. I'm gonna write this out in better steps. So using the temperature table, so I'm gonna talk this out again. Using the temperature table, so pressure 1 is greater than Psat, which means we are a compressed liquid. We are a compressed liquid. Not we, but which means the fluid is, we are all compressed liquids on this day. Using the temperature P1, using the temperature table, P1 is greater than Psat, which means the fluid is a compressed liquid. And using that, you go to the compressed liquid tables and you go across here at this value, which shows up as 0.0010290. So that is our answer for the specific volume. So let's do that right now. So using the compressed liquid tables, V1 is equal to 0.00. Remember though, because like I said, the table value is divided by 1,000, so that's why I'm doing 0.00 meters cubed per kilogram. So that is our answer for the second part. Does anybody have any questions about that? So once again, the hard part about that was finding if it was superheated or subcooled. And remember, on the pressure table, if our temperature is higher than the one listed, we are superheated. If on the temperature table, our pressure is higher than the one listed, we are subcooled. So they flip. That is why I always tend to use, if I have a choice. So for example, if you were given, say, 200 Celsius and 5 bars, or 5 bar, I will always use the pressure table. Because the pressure table, it makes sense, right? If something's higher, it's superheated, right? That's why when given the choice, always use the pressure table. But the temperature table, you have to know how the relationship works as well. So does anybody have any questions on that before we move on to the next question? Okay, so let's go back up to the table really quickly. Yeah, got it written down. All right, good. So on the pressure table here, do you see so this is the properties of saturated water pressure table. If you have, let's say, 1 bar here, right? 1 bar corresponds to 99.63 boiling point, right? As a temperature. If you use the pressure table, if our temperature given is higher than this, so let's say I give you 1 bar, 200 degrees Celsius, we are superheated because our value for temperature is greater than this right here. But if you use the temperature table, so let's roll back up to the temperature table. If I gave you 200 degrees Celsius and let's say 30 bar, right? Our pressure on the table is 15.54. So if you are greater than this number on the pressure table, you are now subcooled. So the relationship flips. Essentially, for the pressure table, if your temperature is greater than the saturation temperature, you're superheated. If on the temperature table, if your pressure is greater than the saturation pressure, you are subcooled. So you end up on either sides of the extreme depending on what table you use. Or the flip. Essentially, it's the flip. One of them tells you one. Now, really quickly, if you, let's say I had it under here, it would be a superheated. So that's where you have to understand that. So essentially, you have to understand that if it's greater than this number, If your pressure is greater than this number, it is subcooled. Yes. Okay. But that's why I said it makes some. You should use the pressure table when you have it, when you can. If you are given a temperature and a pressure, use the pressure table. Now that question was designed to where the pressure table was not helpful because your pressure was not on here. But if you guys, so you'll get better at this as the classes go on, like doing 300 and 400. But when I saw that right here and noticed that it wasn't listed on here, it immediately screamed to me that this was subcooled, right? But like I said, as you gain more experience, you'll start to be able to tell when something is superheated. Like for example here, part C. I didn't have to look at it to know that it was superheated. I didn't even have to look it in the table because you could tell just like once you start getting more used to the numbers, you'll notice things. You'll be like, okay, this seems really high. So for example, part C, we are given P1 is equal to 10 megapascals. 10 megapascals. And T1 is 485 Celsius. Right? So 485 Celsius. So that's pretty warm, right? Very warm, actually. And pressure is very high. So just to, I guess, give a perspective on that. So 100. So this right here is 10,000 kilopascals, right? 100 kilopascals is atmospheric pressure. So we are way higher than atmospheric pressure. We are high as can be. And if you look at 485 degrees Celsius, that is also very high. So essentially, what it tends to boil down to, pardon the pun, is that if you see two numbers here that are relatively high, like these two, I usually think it's superheated right away. The reason why the last one wasn't superheated was because the temperature is actually low. Relatively low. Like 100 C is relatively low, actually. It's the boiling point of water at atmospheric pressure, but it's relatively low in the grand scheme of things because in most like power cycles, you end up with numbers like this, like really high numbers. So it's actually low. Most power cycles that you see in the world, nothing is at the boiling point. It's way higher than that. Like it's not at 212 Fahrenheit. They're usually thousands of Fahrenheit. So that's how I immediately get like a little picture of where it might be. So let's go ahead and prove that though, because it's great to think about it, but if you prove it, you have to prove it. So we have to go down pressure and bar. So as I said, this right here is 10,000 kilopascals, which is also 100 bar. So if you go down here to bar, 100, right? So 100 bar, and you go over here. So really quickly, Michael, this is all you. You're taking it away here. Because we have a pressure table, we are on the pressure table, we went down to our pressure of 100 bar. Where are we located now? So we're in this column right here, or this row. So where are we located? Or Tanner, you can tag in as well. Anybody? Yes, which means that we are what? We are superheated, correct. So, because we are on the temperature or the pressure table, how you compare it is you go to your pressure line. So go use the pressure table to obtain a value for Tsat. So our value of Tsat, which is, like I said, the saturation pressure, which is equal to 311.1, right? C. Then we do our value, so T1 is greater than Tsat, which means we are superheated, right? Because we're using the pressure table. So that, like I said, that relationship hasn't, it's not flipped because depends on where you started. But essentially, for pressure table, it is superheated if you are higher than that number, okay? So if we know that, and we know that we are superheated, our next step should be to go down to the next table. So the superheated table, use the superheated table to find V1 to be equal to. So I will do that in a second. So let's scroll on down. So here is the properties of superheated water vapor, which is the superheated tables. We must find 10 megapascals at 485 degrees Celsius. So we got to scroll down just a little bit here. I think it's on, oh, here it is right here. One more down. 10 megapascals right here. So 10 megapascals, and then we have to go down to our temperature, which right here it says 480 to 520, so our number is in between. So right here you could interpolate, or what you could do is, what I did was, since I didn't interpolate, you could just look at these two ranges, and you could go, okay, you know, it's, you could use some basic, like, you know, midpoint kind of like averaging and things like that if you wanted to. What I ended up saying mine was equal to was, I said my volume, which is, remember, in this column, meet it up with 480. So the 480 degrees Celsius one is 0.03160. I said mine was equal to, I don't know what the, I actually do know what the, I'll have to look at the actual answer, I guess, but I'm pretty sure it was interpolated. I said this. That's what I said, but I'll have to actually see here in a second what the actual number is. Let me see. It says that oh, that's got to be a mistake. Yeah, that answer's wrong. Yeah, their answer's wrong, actually. Huh, okay. Yeah, so their answer's wrong, and I think it's wrong because so if you guys look really quickly here, you'll see that as from 480 to 520, the number gets bigger, right? So if you see here 0.03160, it gets bigger to get to 520, right? Everybody, you guys can see that? Right here. So the specific volume gets bigger as you move down the table, right? Their number is actually lower than this number. It's lower than the 480 degree Celsius one, and ours is 485. That's can't be. It can't be. It has to be larger than this number because this is the lower level limit of it. So their number's wrong. But what I would say is anything from here down, like you could make a reasonable estimate in here. I don't require you to interpolate on exam. So if you just took a nice guess and said like, I don't know, 0.032, I would probably be okay with that. So I'm not too worried about it. But I'll have to interpolate that and figure out why that's wrong. What they did wrong. All right. Are there any questions on that one before we move on? Because we do have to hurry up. This is the last one. All right. So I'm going to go ahead and start. So we're on the last one. So we have temperature equals 80 degrees Celsius and quality is equal to 0.75. So this is what we know. So T is equal to 80C. And we have X1 is equal to 0.75. So we were given a quality and a temperature, right? So if you are ever given a quality in any part of the problem, that state that it corresponds to is saturated. It's in between the curve. It is under the umbrella, right? So we already know that this is saturated because we are given a quality. A quality doesn't exist outside of the saturated curve. We are now under it. We have to be under it. So because it was given to us, we know it's saturated. We don't have to do any more work. Except that we now have to go to the table because remember, our goal is to find specific volume, right? So we have to find specific volume. And to do that, we have to know its limits. And its limits are Vg and Vf, right? Because remember, the equation for specific volume is the following. Times Vg minus Vf, right? And so we have to know Vg and Vf. And so we have to go down to the 80 degrees Celsius part table in the temperature table. So we are in the temperature table. We went down to 80 degrees Celsius, which is this line right here. So If you look here, we have saturated vapor of Vg of 3.407. We have a saturated liquid of 0.0010291. So I'm going to go ahead and fill that in. So 0.0010291. Right? Times our x value of 0.75 times our other values, our Vg value of 3.407, and then subtract off what we did at the other one as well, the Vf value. And let me extend this really quick. Okay. And if you do this on a calculator, which I assume you will, if you do this on a calculator, what you will end up with, which I believe I got as something like this, 2.556 meters cubed per kilogram. Okay, which I believe is the right answer. Let me see if I have that on my paint one. Okay, I think I do. So let me back it out here. Now we don't need the tails anymore. So I'll show you guys the answers so you can go back on the video if you want right here, and it kind of explains how you do them as we move through. So right here is the answers to this question. Now really quickly I'm going to draw the charts for them. Okay, so I'm going to really quickly just do a little chart. So this one will be for 1, 2, and so you guys I think have to do this in your homework if I recall. Okay, we're out of room. I'll do the last one up here in the corner. How about that? And I'll label them at the end as well, so you guys can notice which ones we're doing. All right, so really quickly, these are all I think they did TV diagrams, right? So we have T, V, T, V. So temperature specific volume diagrams. So this is A. I'll just use the other tool. That's not going to work, is it? Text tool. A. B. C. And the last one, I think you guys can figure that out. D. Okay. So for this one, I'm going to use a little black ink here. Actually, yeah, we'll do red. So you have to draw the saturation curve, which mine is going to be probably bad. So this is how they should all look. A little saturation curve in every one of them, right? All right. Now, so the first one, really quickly, we found that it was a saturated liquid, right? It was not a saturated liquid. It was a saturated mixture. It was in between the saturation curve, right? Because our value of specific volume was in between Vg and Vf, as said by this equation right here, at temperature 1. So our temperature 1 value was 140 degrees Celsius. So it doesn't really matter where you draw this, but I'm just going to put mine here. So that is T1. T1 is 140 degrees Celsius, and I'm going to do that. Draw a little draw a little line here. Let's do that. So that right there is where we are on the saturation curve. Once again, it doesn't really matter where you draw it as long as it makes sense, right? Like for example, if you have a lower temperature higher on the chart, it doesn't make sense. But it doesn't really matter how you do it. All right. And then lines of constant pressure go down like this. Or actually, no, they don't. They go the opposite way. Apologies. They go up this way. So this line right here is our saturation or our pressure, which is 3 point something bar, which is right here, 3.613 bar. So right here is where we ended up. So I'm going to draw a little dot where we are. Remember, because we ended up, if you did the quality for this first part, you would find that we were 98% vapor. So you end up, we're basically right on the borderline there. We're like right here, essentially. Right on the border. So that is where our state point is. That like little dot right there, which I will. That is where we ended up, right there. And this is our temperature. Our temperature is 140 here. So we are on this temperature line all the way through until we reach out of it, and then we would get higher. But right now we are not, because we are in the saturated region. All right, and so for the next one, this one is a subcooled, right? So we are subcooled. So let's do another one. Let's put 100 degrees. I'm just going to once again draw a line somewhere. It doesn't really matter where. So we're going to draw 100 degrees would be on that line as well, but we are not on that line, actually. We are down that line further. And so, let me go ahead and do this one. Now, this is actually a trickier graph because our pressure is higher than the critical point. So that is why our this one's actually a lot more tricky of a graph to draw. So it goes something like this. I didn't mean for it to end up like this, so I apologize, but I didn't think they would give you a question so really hard. But essentially it looks more like that. Because if you guys realized from the superheated table, your pressure wasn't on here, and that's what it means. Essentially, our pressure is higher than the critical pressure. So our pressure is actually outside of this region. And so it looks something like this, obviously drawn a little bit better. Sorry to say. But you will never have to deal with this in any question in this class. So this, except for this one, I apologize. I did not think it would be like that. But right here, the intersection between those two is where we are currently located, which I will put a dot there and fill it in with some black. So we are right there. So we are at 100 degrees, so temperature of 100 C. So we are at 100 degrees Celsius right there, and we are on this line of constant pressure of 300 bar, which that line of constant pressure is going above the critical point because it's higher. The critical point of water or the critical pressure of water is 220, so we're actually way higher than that. We're supercritical. So this is what this one should look like. Next one, once again, sorry this is taking so long, but next one, we are on the superheated one, so we have to go to 10 megapascals, 480, so I'm going to put 480 way up here, even though it doesn't really matter where you do it. But let's just do that, 480. Draw our lines of constant pressure. Nope. All right. And so, if you recall, since our value is greater than temperature saturation at our pressure of 10 megapascals, because 480 is greater than 311, we are superheated. So our value is a lot higher. So essentially, the saturation pressure is where I drew that first line. Our value of our temperature is actually up here. So it's like up here at the top somewhere. We are at that intersection. This value of our saturation temperature is right here at 311. So essentially 311. So if you were following this pressure, let's just say this. If you were following this pressure of 10 megapascals, it would go up until it reached this point, right? And then it would turn, so it would go up into a temperature of 311. It would stay 311 until it reached here, and then it could be allowed to go higher, which is what happened, right? We are now at 480 degrees, or 485, so we have actually is higher than that point. So this right here is our top temperature, which is 485, right? So we have 311 here, which is the saturation. 485 is the top one, which is where we ended up in the superheated region. Now the last one. Over here, we have quality of 70.75, which means that we are inside the umbrella once again. I'm going to draw our line here, which is where we're going to start. So that is our temperature of 80. So 80 is that line, first line I drew. ADC. ADC, which is that first temperature. ADC is there, right here. And since we are inside of the saturation curve because our quality is 0.75, that means that we are somewhere in here, which I will just draw a line right there, or a little dot right there. It doesn't, that right there is just our quality of 0.75. There's nowhere else to draw that. Like, you can't fix this location any more than that. It's just 75% of the way to all vapor. So this right here, let me zoom in a little more for you guys. This right here are the TV diagrams for each problem and all the answers to the problems. So if this didn't make sense to you in any way, I recommend going back and doing some more practice questions. I can post some if you want. Also, your homework requires you to do this on your first, I think, 2 questions. It has you find properties, so I would definitely go ahead and start doing that now if you're not, because it's due in 2 days. So might want to get a head start on that one. But if you don't have any questions, I'm going to go ahead and take attendance, and then you guys can go. Yeah, sorry for the length of time you were here. That's right, I gotta turn this off.